So it's kind of rule, the presentation can
Yeah, they know.
question 5 minutes, what is still the same.
Okay, so you know the rule. 10 minutes to present your work, 5 minutes for the question. So make sure you stick to the 10 minutes.
How is the people of the less important slide? Is that alright?
As long as you stick to the 10 minutes.
Alright.
Right, you can start.
Alright. Good morning, thank you all for coming. I'm Stefan Nobody, and this is the presentation of my project, optimization of the hydrogen fuel cell in vehicles, or the hydrogen fuel cell vehicle. My supervisor is Professor Andre Orlis. The contents I will be covering is fuel cell vehicles, fuel cell how they work, hydrogen generation, solar panels, calculations I went through, and some electronic designs I made. First off, fuel cell vehicles. The current commercial one available is the Honda Clarity. That's what I based most of my designs on today. It has a tank capacity that lasts 270 miles. It has 136 horsepower, and it can accelerate quite quickly to 60 miles an hour in less than 9 seconds. Some quotes from Top Gear that they said during the show from Jay Leno as a guest star. He said, the fuel cell vehicles are the savior of the car, like the automobiles are the savior of the horse. And from James May, using batteries, which take hours to charge, is a step backwards in car evolution compared to a fuel cell where you just refuel at the station. My aims with my dissertation is to generate a combined system of fuel cell vehicle that produces its own hydrogen on board and through renewable energies obtains that hydrogen. First, looking into fuel cells, they are largely thought of as batteries that use hydrogen as fuel. You have on the left side the anode, which is where the hydrogen is let into, and the cathode is where the oxygen is exposed to, and how they are both separated through an electrolyte, which doesn't let electrons pass through. So what happens, the hydrogen wants to react with the oxygen, but it can't, so it splits up the proton and the electron. The proton easily passes through the electrolyte, whereas the electron gets diverted into a circuit where it then generates a current. Stack more of these together, and it's like a battery, increase the voltage. This is the fuel cell stack using the Honda Clarity. The fuel cell lab, which I performed here at the Roehampton campus using this machine. It's an advanced machine that powers itself with the electricity it generates from the fuel cell. It generates an 11 volt maximum output, and it shows two operating methods, a characteristic and a characteristic assisted with a fan. As I noticed from the results, the fuel cell heats up quite quickly, and so the fan is required to keep the fuel cell operating over time. As you increase the demand, the voltage increases as well, is what I also noticed from these results. And from the temperature, I had to cool it down with a spray of distilled water as to not burn out the system. The hydrogen is generated through electrolysis. It's achieved by passing a current through water. Through the currents, the H2O, it has to be distilled water. It splits into its components, oxygen and hydrogen. And since it's H2O, you get double the amount of hydrogen compared to oxygen as a result. Some energy density tables. Hydrogen has a much higher specific energy compared to gasoline and batteries, which means that it weighs a lot less for the same amount of energy, but the energy density is lower compared to the gasoline, which means it takes up a lot more space. Now this is hydrogen compressed to 700 bar, which is the standard for hydrogen used in the automotive industry. How do we achieve this? I looked into an electronic compressor that compresses it down to 700 bar using current flow. This compressor is 70 to 80% efficient. So for calculations later on, I'm taking a 75% efficiency. This, as can be seen, is very small in size and doesn't take up much weight. Solar panels that I started to look into are monocrystalline panels, which are the very first designs, and they are made using very pure silicon, which makes them very expensive, but due to that they have the highest power output. The next are the polycrystalline panels. They are a greatly reduced cost compared to the monocrystalline, since the silicon they use is a lot less pure compared, but in return the efficiency is 80% down to the monocrystalline version. And then I found something called the hybrid photovoltaic thermal solar panel, which functions just as monocrystalline, but it takes all the thermal generation and uses that as an alternative energy source, which means it reduces the heat in photovoltaic generation, which improves further the photovoltaic efficiency. And heated water can be used within the system, which improves the efficiency of the electrolysis. These are some calculations I went through using fuel cell efficiency, solar panel energies, rim sizes of the car. And as a result, I came to an estimation that with this combined design, you get 100 kilometers of free driving every day by parking in the sun. Next, I looked into solar generation. It's most efficient when a panel is pointed directly at the sun. Obviously, if it's at the roof, it's only vertical, which only leaves 1 hour a day where it's most efficient. So I designed this circuit here using 4 light sensor inputs. They are on each side of the car, north, south, west, and east. And they go for a comparator circuit and logic circuit, which takes them all into 4 outputs, which are only one of them will ever be high, so it becomes a digital output. And here's the truth table for the outputs. These then go into a microcontroller, for which you can see the program here. I've used a Pickaxe microcontroller, which I have used for many years now. And what this does is it takes all the inputs and it checks and it raises the motors dependent on which input is high, so that it always faces the solar panel into the direction of the sun when the vehicle is parked. I then took the electronic design and simplified it down, and I'm using variable resistors instead of a light sensor for demonstration purposes, since light sensors are very difficult to demonstrate with. And I reduced the input from 4 inputs to 3 for simplicity reasons. The finished design came out looking like this. And here's a demonstration of the design. These lights here, the red one on this one symbolizes the motor raising up, and these yellows signalize the motor raising down. So as you increase the light in one, they change, so that one motor, the other motor raises up and the other 2 raise down. But if the other one increases even further, they change again, so that the motor in the center now raises up and the other 2 raise down. And the third one will then produce the same. So this circuit is a control system to always point the solar panel in the direction of the sun while the vehicle is stationary. Next up, this is my completed car design as I would expect it to all look like. I used the Honda Clarity as a base model, and what I added to it are a distilled water tank from the output of the fuel cell, reflow electrolyzer, which then converts that water into hydrogen. So that then goes into a hydrogen tank, which flows into the hydrogen compressor, which pumps it further into the hydrogen high pressure tank already present. Also present are the monocrystalline solar panels and my designed solar panel circuit to improve the efficiency of the solar panel. And that is the end of my project so far. What are the next steps in the project? To further increase the complexity of the solar panel design to give it more than 4 degrees of freedom, to have it go for a more advanced control system to align it perfectly to the sun. Another step would be to component fit all the components included in the design into a chassis to make sure everything would fit inside. And the last thing I can see doing is looking into the use of a photovoltaic thermal hybrid solar panel instead of the monocrystalline solar panel to also heat up the water produced by the fuel cell to improve the efficiency of electrolysis. That is the end of my presentation today. Thank you for listening. I'll to answer all of your questions.
Okay, right, okay, thank you very much. Right, so we have some few questions for you. How you want to make it now?
Okay, quite interesting to cover very widely. Can we explain, if I understood you properly, you want to use use solar cell
Yeah.
to generate electricity, then the electricity will be used to generate hydrogen,
Yes.
then to power the fuel cell. Why you want to use that design, not directly?
Use the fuel.
Yeah, we just store the electricity and use it to directly power them.
Yeah.
What is the logical behind it?
Because the problems with batteries these days are the efficiency of batteries over time. They constantly degrade. There's a drop in power output as the battery level decreases. With a fuel cell, the power output will be completely the same until the last drop of hydrogen is passed through the fuel cell. So it improves the constant efficiency and it improves storage rate since a battery degrades over time, the amount of power it has, whereas a fuel cell with hydrogen, it's in the tank, it won't go anywhere, you will always have the same amount of hydrogen. So I think that it's a much better way of storing fuel in form of hydrogen than in the form of a battery.
Okay, right. I have a question related to this one. So,
Yeah.
because you are using a combination of solar panel and fuel cell, how do you define the efficiency of this combined system? Did you try to work it out?
In the calculations here, I took the efficiency of the solar panel and I took an estimate of how much power is generated through solar panels in the UK per day on average. So it's taken this is from a study from one of our previous project that took a monocrystalline solar panel and aligned in one direction for 1 year. He took all the readings of power it produces a day and he took that to an average of 5.45 kilowatt hours per square meter of area a day. And for the fuel cell efficiency, I researched into the average efficiency of conversion, and that comes up as about 50%. So I then multiplied the 50% by the output kilometers a day, which reduces it to just about 100 kilometers a day.
So what is the overall efficiency of your design, the system you design? What is the overall efficiency?
The efficiency.
Become more efficient. Did you try to work it out? Because one thing you want to show that your system is efficient as well.
Yes, give me a second. It is about 35% efficient.
Right, okay, that's 35%.
But that includes everything, the solar panel, the conversion to hydrogen, the compressing, the fuel cell efficiency and the electric motor efficiency. Combining all these together makes the electricity generated by the solar panel 35% efficient in automotive driving.
Next one for your design.
Yes.
And control. That's correct. The design, that's, if I understand it properly, that's the design. Just for tracing the sun.
Yes.
So to driving the motor and directly towards make sure the solar panel over perpendicular to the
Yes.
to the sun. But you based on the power, how or can you describe a little more about how it works?
How it works? Alright, I'll take this circuit here. These are light dependent resistors. They are a resistor that changes its value dependent on the amount of light compared to another resistor here on the side. Depending on the light level, the resistance changes, which changes the voltage that comes through this line. This then goes into an operational amplifier which compares the two values that come in. Dependent on which is higher, if it's an output of 1 or 0, it then transforms it from this side into a logic circuit. This logic circuit then goes into a gate system, a logic system that compares all these values together and brings the 4 analog inputs of right sensing and brings it to 4 independent logic outputs, and only one of them will ever be high.
And you supposedly that's controlled when the vehicle standing steady.
This is only for when the vehicle is standing steady, since the car will always be in a different position when it's parked. It can never be assumed that you can just raise it in one direction. So it's most efficient to sense where the light is most coming from and to raise it in that direction.
Thank you.
You mentioned somewhere in your presentation that you need a fan to cool down your.
And to cool down the fuel cell, yes.
So how do you size this fan? What is the power for this fan?
I've not looked into that yet. There's just a realization I came across. I didn't know a fuel cell produces that much heat until I ran the experiment a few weeks ago.
So in your opinion, if you have to find the size of this fan, what would you do then?
You have to see how much airflow is needed to reduce the heat in the fuel cell. And there are probably already calculations done, as can be seen in this image here. There already is a fan present right here at the front. This is a fan that's pulling the engine and the fuel cell in conductivity. So it already is present in the fuel cell vehicle at the moment.
Okay, good. Any questions from you guys then? No?
Yeah.
What engineering are you studying?
Mechanical engineering, but my speciality is mainly about electronics. And hopefully next year I'm going into a master's for mechatronic systems.
Okay, good, very good. Next one, Peter.
Yes.